All right, looks like the numbers are stabilizing, so let's go ahead and get started. Welcome to today's CNCF webinar, Planet Scale Machine Learning Workflows with Advanced Data Management on Kubeflow. I'm Caitlin Barnard, Marketing Manager at CNCF, and I'd like to thank you all for joining us today. I'd also like to welcome today's presenter, Bengaluru CTO and co-founder at Aricto. So just a few housekeeping items before we get started. During the webinar, you are not able to speak as an attendee. There is a Q&A box at the bottom of your screen. So if you have any questions that come up throughout the webinar, please feel free to drop them in there. And then we'll hold Q&A until the end and get to as many of those questions as we can. This session is also being recorded and will be sent out along with the slides after the presentation. So with that, I'll hand it over to Bengaluru to kick off today's presentation.
Thank you, Caitlin. It's a great pleasure to be here today. Nice to meet you all. I hope you enjoyed today's seminar. So as Caitlin mentioned, I'm Bengaluru, founder and CTO of Aricto. What we're doing at Aricto is planet-scale data management, and we focus on Kubernetes and ML environments. So let me make sure I can switch to our slides, share my screen. You should be seeing the slides.
Yep, we can see them.
Great. So today we'll be talking about planet-scale ML workflows with advanced data management on Kubeflow. What does that mean? It means we'll go over what planet-scale means for us. We'll talk about machine learning on Kubernetes, Kubeflow, which is the ML toolkit for Kubernetes. Focus on how managing data is very important for efficient machine learning. Talk about data management in Kubeflow, which is the area in which we have made a few contributions to Kubeflow, and demo the platform end-to-end, Kubeflow, along with our integrations. So by now, it's a definite fact that we live in the Kubernetes era. Kubernetes has become the default container orchestration engine. No one can question that anymore. Across platforms, across different kinds of infrastructure, Kubernetes is the single, simple way to declare your containerized infrastructure, and then the underlying platform does whatever you ask it to do. But this is a CNCF webinar, so there's no reason for me to argue for Kubernetes. We are already sold on this. The question is, what happens with machine learning now that Kubernetes is gaining ground so fast? So although everyone is doing their own thing right now, we believe that eventually ML will run on Kubernetes with Kubernetes primitives gaining all the benefits that Kubernetes brings. With Kubernetes primitives means that machine learning will be running in a declarative way. Users will be declaring to Kubernetes the kind of ML infrastructure they need, and Kubernetes will make it happen. Users will have a single way of asking what they want to have across infrastructure, across locations, and Kubernetes will make it happen. And because users cannot really, don't really have to speak to Kubernetes directly because they're ML users, the data scientists, what do we need in between? We need Kubeflow. That's the overall idea. So why should ML run on Kubernetes? Because this will bring containerization, better, more efficient handling of hardware resources, auto-scaling, portability across locations, across infrastructure, extensibility, and no vendor lock-in. So we're just getting started on this. But the very good first step is Kubeflow is here, and Kubeflow is the ML toolkit for Kubernetes. It is the first native machine learning toolkit for Kubernetes, announced by Google just over a year ago, end of 2017. It is already picking up speed to become the de facto ML platform. It's a way of declaring your ML platform using Kubernetes primitives, using Kubernetes components. So I will spend the next few minutes with some slides I got from a presentation by Jay Smith and David Aronchik. David Aronchik is the co-founder of the Kubeflow project. This presentation was given in KubeCon North America 2018 in Seattle last December, Machine Learning as Code, to essentially introduce Kubeflow to those of you who may not have heard about it before or who may need a quick recap to get up to speed. So when people think about machine learning today, a big mistake many people make is that, well, we need a data scientist, and this data scientist is going to build a model for us, and this is ML. Well, building a model is part of an ML workflow, but it's not what ML is all about. Building a model is just one step in a very big ML workflow. It's a multitude of components that we need to take care of and we need to stitch together to have a working ML pipeline end to end, from an initial data set that we have to ingest, we have to analyze, we have to transform and validate and split, and then we have to train an initial version of our model and validate that it works, and maybe it doesn't, so we have to go back and train it again and modify it. So it's an iterative process. And then we have to train at scale. And when we have a model that's been trained at scale and works, we have to roll it out and serve it in production. And then we have to monitor it, and then we have to log its progress, and then we have to go back and fix things. So from the initial data to having a model running in production, there's many steps. And these steps sometimes have to happen in different places and sometimes have to be executed by different people, different personas. So this becomes a very complex stack, and it requires expertise in a multitude of layers, because it's not just the top layers that the data scientist or the data engineer would care about. It's not just the framework and the tooling and the UX and the model building. It's also the lower level things. What about my runtime? What about my drivers, my operating system, my GPUs, the hardware I will run on? How do I scale my infrastructure? So this is complicated enough, but then given that different parts of the workflow will run in different places and you need to replicate all this. So what we talked about so far is the upper layers. If you have to replicate this for experimentation, locally maybe, on my laptop, and then to train at scale in some bigger infrastructure, and then to have the model running in production on the cloud, I have to replicate all these layers. How do I do that? So the first step is, let's stop thinking about these lower level hard layers. Let's get Kubernetes to take care of them. So Kubernetes takes care of the low level handling of the runtime. So Kubernetes is the platform on which I run my machine learning. So now I can move from location to location and from one kind of infrastructure to another, from one cloud provider to the other, with Kubernetes being the single language in which I declare my infrastructure. And then let's get Kubeflow as the single way of developing, deploying, and managing machine learning on Kubernetes. So let's get Kubeflow to be the single language in which I describe to Kubernetes my machine learning infrastructure. So again, Kubernetes takes care of the lower level stuff, and then Kubeflow becomes the language in which I declare the way I handle my steps in my ML workflow. So Kubeflow becomes this part, and then I have Kubeflow everywhere, so my job is much simpler. I use Kubernetes in all locations, and then I declare my machine learning infrastructure using Kubeflow. That's the basic premise behind Kubeflow. Okay, so Kubeflow and Kubernetes, in our view, are pivotal in enabling next generation machine learning. And what do we mean by next generation machine learning? We mean the ability for distinct roles the data engineer, the data scientist, the DevOps person, all interacting across locations to make this workflow function. So we need collaboration. We need different people doing different parts of this workflow and still being able to collaborate in a way that's reproducible. What does reproducible mean? That when someone has a step completed, some other person can hand it over to some other person can take over their work, and they can reproduce their exact state so they can continue the workflow. We need a simple, streamlined, unified workflow from the first pre-processing steps to developing the model, to training, to getting to production, from my laptop to the cloud, to the autonomous car maybe, where the model will eventually run, where inference will happen. And ideally, in next generation ML, we would like everything to execute fast. So the question becomes, where is the data for the steps to happen? The data should be ideally local. If I keep the data somewhere remote on a slow data lake, if I depend on a single slow object store, then no matter how many GPUs I have, how fast my infrastructure is, I will be bound by data access latencies. So this is where we as Aricto come into the picture. And this is how, this was the trigger for our involvement with Kubeflow. The question is, how do you manage data for this ML workflow when this data has to be in multiple locations? How do you manage data in a pipeline that runs across locations? Because an ML pipeline is as good as its data. So I'll spend the next few minutes describing who we are. We come from a systems engineering background. We work mostly on data management for Kubernetes. Our involvement with Kubeflow is contributing code to it. So Kubeflow manages data as Kubernetes native resources. And then if Kubeflow manages data as Kubernetes native resources, our software can sit on the side and provide efficient data management for these resources. What we do explicitly is we allow you to snapshot, version, package, distribute, and eventually share with others your full environment, your resources on Kubeflow, along with their data. So this makes the pipeline, the ML workflow, work across teams, across locations, and across different kinds of infrastructure, on-prem or on the cloud. This is the overall idea. Initially, you have some sort of experimentation locally. You do it on your laptop. So you run Kubeflow. And Kubeflow is extended so it becomes data aware. It stores your data on Kubernetes objects named persistent volume claims. And then these persistent volume claims are stored on whatever storage you happen to have locally, your local disk. At some point, but this is a full single Kubeflow way of describing your pipeline. So you use the exact same primitives, the exact same APIs to do your job. And then when you're done, you or another person uses Kubeflow again to spin up the exact same pipeline on another location for training on the Google Cloud, for example. Our software sits along Kubernetes to enable this kind of interaction. So our contribution to Kubeflow is twofold. We extend it so it works over PVCs, and then we use our software on the side of PVCs to enable cross-location collaboration. This is the overall picture of what I will be demoing to you today. What you get with this is a way to version, package, and distribute your data, and then you can have a unified hybrid pipeline that works both on-prem and on the cloud. And because we work with snapshots, because when we move data, we essentially snapshot the data, you can always go back in time and see what the state of the pipeline was. So you can always reproduce it and try again and come back to the exact state where you were. I've talked a bit about these things, but it's best if we can watch it live. So This is the demo that we'll be doing. We'll have a machine learning pipeline, same as I showed before on Kubeflow. We have two users, Sarah, which will be doing the experimentation part, the data ingestion and pre-processing part in location A, and James, who will be doing the training part on location B. So he'll build a model and train it. So given this ML pipeline, Sarah will essentially be doing these steps, a bit shortened, and James will be doing these steps. And for this, we'll use an example that the Kubeflow community has created called the GitHub issue summarization example. This example is a machine learning pipeline where we get data from GitHub, issue data, issue text, and the model tries to create a summary that describes the content of the issue as good as possible. So let's start with this. I'll use two locations. This virtual desktop is location A. It runs on Amazon in zone US West 1A. It runs Kubeflow on Kubernetes. And this desktop will be location B. It runs on Amazon again, zone US West 1B, running with Kubeflow. So this is where James is on B, and this is where Sarah is on A. So what does Sarah do? She uses Kubeflow. She starts a Jupyter notebook. A Jupyter notebook is a very well-known development environment for ML. So she logs into Jupyter Hub using Kubeflow. And she will be creating her notebook. Okay, so she needs a development environment. She'll use a standard image. She'll request 2 CPUs, 8 GB of memory. What about your data? She'll have a simple workspace where she'll store her code and her libraries mounted here. And she'll also use a data volume. Let's call it GitHub data, 10 GB in size, which will be mounted here. So Sarah will be managing her data as another locally mounted file system. This is backed by a persistent volume on Kubernetes. So Sarah creates her notebook. So what happens here is Sarah uses Kubeflow to allocate a new development environment for her to do ML. And this development environment will be a Jupyter notebook. We give it some more time. Underneath, what happens is Kubeflow asks Kubernetes to create a new pod to serve Sarah's notebook. And this user interface, managing data volumes, was one of the first contributions we did to the Kubeflow project. So this is Sarah's development environment. She has her data volume where she will store her data. She has the ability to start terminals, create notebooks. So let's start a terminal. And what we'll do is increase the font size a bit. Get it full screen also. Okay. So we will clone the issue summarization example from Kubeflow. So Sarah brings her code here. This is her code. Okay. And this is where she will store her data. This data volume is backed by a local ephemeral NVMe disk, SSD, on an Amazon EC2 instance currently. So Sarah stores as fast as she can with minimal latency to a local disk, so she can work as fast as she can. This could be her laptop even. She's working on her laptop and storing to her local hard disk. Okay, so let's say Sarah needs to install a few missing libraries before she starts. So she can install missing libraries. So she can do machine learning inside her development environment. And these libraries become part of your development environment managed by Kubeflow and us. So she can install her libraries as well. Okay. And now she starts with a notebook. We already have a notebook to start from. We won't be creating it from scratch. This is the notebook we will be using. So Sarah can now import her libraries. Okay. And now what's the first part in an ML pipeline? Sarah wants to experiment. So the very first part is, let's get the data that we're going to be using into our development environment. Let's ingest the data into the pipeline. So Sarah has this empty directory where she will store her data mounted onto her pod. She remembers it in a variable, and she uses wget to fetch the issue data as a big zip file somewhere from an external data lake. So this is the first data ingestion part. And then once she's brought the data into her environment, she will also uncompress it. She will unzip it. So this is an initial data transformation step. So Sarah runs wget. She goes to the external data lake, fetches her data into her environment. This is quite fast because all storage happens locally. And then she unzips the zip file to create a comma-separated values file, a CSV file. This is not a small data set. This is in the order of 3 gigabytes data set. Let's take a look. So it's a 1 gigabyte compressed file, and it will expand to about 2.8 gigabytes total. So this is done. Sarah pretty quickly stored 4 gigabytes of data in her environment. So going back to, oh, I apologize. Oh, I keep clicking the wrong thing, I'm sorry. Okay, going back to the notebook. So Sarah has unzipped the data. She has done an initial transformation step. Okay, let's assume this is the first step of the pipeline. So let's assume Sarah has completed up to the ingestion, analysis, and transformation part. Okay, now at this point, she may want to hand over her work to somebody else, or she may want to take a snapshot of her work so she can go back in time and review what she did. Okay, so for this, because all data is stored on a Kubernetes object, a persistent volume, we can use our software to take a snapshot of the whole infrastructure. So let's take a quick tour of our software. This is Rock. This is what runs alongside Kubeflow and is integrated with Kubeflow, so you can manage your data across locations. So this is Sarah's deployment on her local infrastructure. There's 2 buckets, Sarah's bucket and James' bucket. Buckets is where we keep all user data, snapshots of full environments. Let's have a look in a previous bucket. This one, for example. It contains a few snapshots of environments we took previously, some time ago. Each environment is a snapshot of the workspace volume where Sarah keeps her libraries, and the data volume where Sarah would keep her data. So an environment snapshot is a group of 2 snapshots, the workspace snapshot and the data snapshot. And then for each environment, we can have multiple versions. So you can go back in time and see what your environment looked like 10 minutes ago, 20 minutes ago, or a week ago. So it's essentially a time machine for your full environment based on snapshots. And this is how we enable the pipeline to span multiple locations. We move the pipeline state from one location to another to allow it to move from location to location. So these are pre-existing snapshots, older ones. Let's see how Sarah can go into her empty bucket, no files here yet, and ask for a full snapshot of her environment. So Sarah will snapshot her full lab. She'll snapshot both her workspace and the data. This is essentially Git-like. Sarah commits her full environment into our software, into Rock, including the data she just downloaded. So ingress data, unzip into CSV, ingress data into gdata, run initial decompression step. These are notes she keeps for herself in the commit message, okay? And at this point, what happens is our software creates an asynchronous task that gets to the Kubernetes native objects, the PVCs that Kubeflow has created, and takes a snapshot of them. So we take a snapshot of whatever libraries she has created and whatever data she has brought into her environment. And it's interesting to note that we do it thinly. So we know what parts of the data set have changed, and we only read the changed parts. So if you look at the data volume, she has brought in more or less 4 gigabytes of data. That's why we're reading this many data pieces. Next time Sarah wants to take another snapshot of her environment, this is going to happen much faster because she won't have touched as much data. So we give it some more time. And her snapshot is done. So Sarah now has a full snapshot of your environment at this point in time, containing your data volume and your library volume. This is it. And now she can continue. Now she can pre-process the data. Okay, so she will split the data into a training set and a test set. We will use a limited sample size of 200 samples, so it executes quite quickly. So this is the pre-processing part now running. Again, this runs over her local SSD, so it's as fast as possible. We read a full CSV file into memory and split it. So we can assume that Sarah essentially runs the data splitting part here. Okay, this is a sample of our issues, the data we're working with, and then we do some more conversion into data structures so we can continue with our training, and then we do pre-processing, again following our notebook. We import libraries, continue working, instantiate a text processor. We have our text processor. Okay, we have pre-processed our data, a small sample of it anyway, so it finishes quickly. And now we'll serialize everything to disk. So at this point, Sarah will dump the pre-processed state into the data volume. She'll dump files into her mounted file system. Okay, so this is the result of the data pre-processing step. So if Sarah goes to the data volume, we see that we have the original data set as a zip file, unzipped, and then we have the result of the pre-processing step. So at this point, Sarah is done with the pre-processing step. She has a trainer already. It's part of the notebook. So we're done. We now need to build the model. So we need to move the pipeline now so James can work. James has to start from where Sarah has left the pipeline. Or Sarah may need to come back to this step if things fail and try over or modify a few parameters or try out some new things. And she needs to do it in a way that's reproducible. She needs to know exactly what she did to reach this point. So what Sarah will do again, after having completed pre-processing, she will go and get another snapshot. So she uses our software to snapshot her full environment again, pre-processed data, dump to disk. So she has completed the pre-processing step, and she has dumped all state to this volume. So she takes another snapshot. This time the snapshot will be way faster because she didn't actually touch all of her data. We will detect that she has only inserted new state in her volume, the pre-processed data, and this is done. So now Sarah can go back either to this state or to her previous state before starting pre-processing. Okay? And now that we're here, we can move the pipeline to James. So James will reproduce Sarah's state in another location and continue with building the model and training it. So Sarah is done. Here's James. James is on a completely different zone, completely different location, and doesn't actually share anything with Sarah. They don't use a single S3 as a data lake to exchange data. James won't go to Sarah to find the data he needs. The data has already been synchronized locally for him by our software. So this is James's view of what's going on. This is the Sarah bucket. It already contains data on his side because our software took care of synchronizing it. Here's more information on this. This bucket, Sarah, actually has two connected peers, two locations. One is James's location, 1B. The other is Sarah's location. If 3 or 4 or 5 people or 5 locations were involved, you'd see 5 items here. Underneath, we do peer-to-peer synchronization of these buckets. So you can have a pipeline that extends to multiple locations, and those locations synchronize data state with peer-to-peer encrypted connections. So James already has the data he needs. This is the data he needs. This is the latest snapshot. If he looks into the file, he'll see that it has 2 versions. The original one, right after bringing the data into the environment, and the second one, right after pre-processing the data. So James can start from the latest snapshot, get to his instance of Kubeflow, log into his instance of Kubeflow, and pre-initialize the environment with whatever Sarah gave him. So what I did was copy the link to Sarah's snapshot from our software and give it to Kubeflow so it can proceed. So here's what James will start from. James will start with 2 CPUs and 8 GB of memory because we maintain all metadata for the environment. So it's reproducible. James will have the exact same environment, pods on Kubernetes managed by Kubeflow. James will have access to Sarah's workspace, so he'll see the exact same libraries. And James will also see the exact same data right before Sarah took the snapshot. Sarah can continue to work in her local infrastructure, can continue to produce snapshots, and James can continue with his branch of the environment. So this is essentially the combination of Kubeflow plus Rock, our software, is Git for data and your whole ML environment. So James spawns the environment. We wait for a few seconds. Underneath, Kubeflow asks Kubernetes to create the pod to support his environment. The data will be stored on Kubernetes persistent volumes. This took no more than, what, 20 seconds? Let's give it some more time. Okay. So this is James's clone of the environment. And we see the environment is already initialized. So he has reproduced Sarah's state. Her code is here. Her data is here, both the original data set and the preprocessed data. So he can pick up and continue the pipeline from where Sarah left it. So what will James do now? He'll train. So let me increase the font size again and get it to full screen. Okay. So James knows where the notebooks live, and he can see the data. This is our 4 gigabytes of data. And now James will use a training module in Python to train his model. This is the training module, and it needs some information. So James will just use the local files that he can see. This is the input data, and he won't be doing any preprocessing because we've already done it. So he doesn't need to use any temporary directories. He'll just train the model into this file for a sample size of 200 issues, because this is the sample size that Sarah used during preprocessing. So now James runs training on a different location, which could be the cloud, using GPUs maybe. We have extended the ML pipeline from Sarah's location into James's location to run training with different hardware or maybe at scale. So James uses the preprocessed data to train the model. We're only using a very small sample size, so training should complete quickly. Okay. And this is the trained model. So James has completed training. And then how can this continue? 2 options. James could spawn a distributed job right from within the notebook using the same primitives, using a snapshot of his environment to power the distributed training job. So he can submit a Kubeflow TensorFlow job object to start a distributed job. Or, and this is what we'll do now, he can take a snapshot of his full environment, including the model, so he can give it to Sarah or some other collaborator, maybe a production person, who would try it out and deploy it to production. So again, now that the model is done, James can go here and request, this is his bucket, request a snapshot of his environment, train the model. So he keeps a note, train the model, sample size equals 200. Model is in this file. Okay. And again, this will start a new snapshot job in our software. Super fast. So at this point, James is snapshotting around 5 gigabytes of data. But this happens very quickly because the software keeps track of what has changed. So again, this is location B. We move back to location A. And Sarah can go to James's bucket. And she can see that here's the data that James just produced. So the snapshot that James took has been synchronized back to Sarah's location, so she can continue, she can iterate on the model within seconds. So we are kind of, at exactly when the presentation should finish. I'll stop the demo here. So we also have some time for questions. I'll hand it over to Caitlin for this.
Awesome. Thanks so much for the presentation. So we do have some time for Q&A right now. So just a reminder, there is a Q&A box at the bottom of your screen. So please drop your questions in there, and then we'll get to as many as we have time for. So a few questions have come in during the presentation. How is Rock authenticated to get access to Sarah's volumes?
This is a good question. Okay, so Rock manages Sarah's volumes. Rock is integrated with Kubernetes as what it's called a CSI plugin. So whenever Kubeflow requests new volumes, it asks Rock to create them, to manage them. So the question is the reverse. How does the Kubeflow user interface, the spawner interface, this interface right here, let me destroy Sarah's environment and show you. The question is, I have to destroy the interface. Anyway, I have to destroy the notebook to show you. The question is, how does the Kubeflow user interface authenticate itself to Rock so it has access to its snapshot? We maintain secrets in Kubernetes. Sarah maintains her own secrets in Kubernetes, giving access to whatever tokens Rock needs for Kubeflow to access it. So the very first time Sarah will access the Kubeflow environment, she'll see a warning message that says, this Kubeflow deployment is not authenticated to access Rock. Please go to Rock, get your tokens, and insert them as a secret in Kubernetes, accessible by the Kubeflow user interface, so Kubeflow can access Rock. So it's not Rock accessing Sarah's volumes, it's Sarah's Kubeflow accessing Rock volumes. Does this answer the question? Can we have back and forth on questions?
Yes.
Sure.
Yes, if you want any information on any of the questions that we're answering, please drop the follow-up question in the Q&A and we'll get back to it. Another one, what does the train Python script run?
Okay, that's a good question. We didn't go into the ML specifics. This repository, the Kubeflow examples repository, is open on the web. So you can either download the original version by the Kubeflow community or our version, accessible here, and see exactly what the script does. The training code is all available right here. Okay, this is the trainer. So it creates the model and trains it, but I'm not familiar with the ML specifics.
All right. So the demo makes it look like the same blocks are stored twice, once for Sarah and once for James. Is that a common thing to do?
Okay. So the question is, Sarah and James work in different locations. Okay. Sarah and James work completely independently. Sarah works on her laptop and James may be working on the cloud. Would they be able to use the exact same block storage? Would it make sense for James to have the impact of latency to go all the way to Sarah's laptop? Would he be able to go all the way to Sarah's laptop to actually fetch the same blocks? So if Sarah and James are working on the same location, they can actually be accessing the exact same blocks. But if you're working across locations, then the question becomes, does your code traverse regions to find its data in another data lake? If you're in an autonomous car, do you access a remote API to find your data? This example and our approach is, let's bring the data set close to where the compute part runs. Let's have the data set be the globally accessible resource, refer to it, and synchronize it locally. Whenever they snapshot, they don't create new blocks locally, right? All the snapshots locally maintain a shared set of blocks. But yes, when talking about distinct locations, because we actually want locations to be independent in terms of security and speed, we maintain two distinct sets of blocks, one for location A, one for location B.
All right. So is there a concept of teams, for example, so that by default, anyone in the team has access to the volumes of other members of the team, for example, to enable access cleanup when a member leaves?
This is a great question. Yes, there is. I didn't show it. We have what we call the ROC registry, the single hub where all locations essentially discover one another, because one question I didn't really go into is, how did Sarah's bucket get to be synchronized with James's bucket? How did the bucket Sarah on Sarah's infrastructure come to be synchronized with bucket Sarah on James's infrastructure? So what they did is they went through a publish and subscribe step on a single data hub that we call the ROC registry. So on the ROC registry, you can define organizations, similarly to how you would define organizations on GitHub. You can share your buckets, your data sets with whole organizations. And then if a person leaves the organization, whatever infrastructure is authorized by them to access this data is automatically thrown out of the synchronization swarms. So you can have members of the team leaving the team, you can have new members of the team joining into the team, and then the peer-to-peer synchronization is updated to take into account your changes to team members. And then this is also a very good comment that I see on the Q&A panel. Snapshotting is not just for sharing. Yes, it's for versioning. If you're local somewhere, if you maintain multiple snapshots of your own environment, even if you share with no one else, even if you're using just a single local data lake, it makes sense to be able to snapshot your environment, because this gives you essentially an immutable Git-like timeline to your work. So when something goes bad, because not everything happens perfectly with the very first try, you can go back in time and reproduce your work. So sharing this immutable timeline across data centers is an extra point, is an extra value-added thing that we do. But even if you keep this inside a single data center, it makes sense to work with snapshots to maintain an immutable timeline of your steps.
All right, there's a couple more that we...
Shall I continue?
Yeah, there's a couple more I wanted to get to from the chat that we answered in there, but I want to get to them live as well. Is the snapshot stored locally?
Is the snapshot stored locally? Okay. Rock, so for each individual location, Rock needs some sort of persistent store for long-term archival of the duplicated blocks. So all the live volumes are stored on Kubernetes persistent volumes. So they're stored on local SSDs even, super fast. It can't get any faster than that. But when you snapshot, Rock deduplicates your data and needs an archival place where it stores your data in the long run. And this is different for each location. So each location is completely independent from other locations. And that's how you can scale to potentially hundreds of locations. That's how this can work across a few thousands of autonomous cars running on the roads, right? So you need some sort of local storage local to the region to store your archived blocks. If you're on Amazon, we use whatever local S3 instance you have. So if you're in US West 1A, we use the S3 region, US West 1. If you're in another region, we use S3 for this region. If you're on Google Cloud, we use Google Object Storage. If you're on your laptop, we use part of your local disk, a local directory. If you're on-prem Kubernetes, we're just fine with using Minio, for example, as an S3 endpoint to store the archived data. So we just need some sort of local archival endpoint where we store the duplicated chunks out of which we form the virtual snapshots.
All right, and then another question. Could you talk a little bit about how Rock is different from something like Rook or Portworx?
Okay, I like the questions there. They're very focused. They're exactly the questions we'd like to talk about. So Rook is a great project for orchestrating storage locally. Rook can create a Ceph cluster pretty easily locally. So you can ask it, I need Ceph to store my local volumes. Okay, so Rook will give you a local Ceph cluster. Then you can have local volumes. So part of our work with Kubeflow is getting Kubeflow to use local persistent volumes. So in this case, Kubeflow would use Ceph volumes managed by Rook to store the data. But then how would you snapshot these volumes so you can go back in time? You could use Ceph snapshots maybe, or you could use our software alongside Ceph volumes to maintain these snapshots. Because once we maintain these snapshots in our own format, then we can take these snapshots and synchronize them in a peer-to-peer network across tens or hundreds of locations. Because if you use Rook to manage a local Ceph cluster, how do you then synchronize the content of this Ceph cluster with other Ceph clusters? You may do, and most storage technologies do, this kind of point-to-point master-slave replication, right? You can have a primary site and the secondary site, and you can be synchronizing your volumes from one side to the other. But this essentially means that the two sides trust one another. And this also means that it's not the user who's in control of the synchronization process. It's the administrator who has set it up explicitly. Our approach is, let's make the data a Kubernetes managed resource, something that the users themselves can actually refer to. And then let's allow the users to specify what gets accessed where. Rook manages primary storage. We do not target primary storage. We do not store your data. So if you take a look at this part of the presentation, we assume that there is some way to store data locally, PVCs. This is our contribution to Kubeflow, making Kubeflow work over PVCs. So this could be Rook and self-provided PVCs. And this could be Rook, any storage. And then our software sits on the side and keeps track of what has been changed and maintains immutable snapshots and then synchronizes these snapshots. And this is this is the same answer as with Portworx. How would this compare to Portworx? Portworx is a very fast, very nice way of managing primary storage on a Kubernetes cluster. But then how do you move from one location to another? How do you synchronize locations that run different kinds of storage maybe? That's our approach. You run our software on the side of whatever primary storage you run on each location. We maintain snapshots, we expose them as user accessible resources, and we synchronize them independently of whatever primary storage does.
All right, awesome. I'm going to get one more in here before we run out of time. Are there APIs to programmatically snapshot the workspace and/or volumes that will allow a CT/CD pipeline with minimal manual interventions?
Okay, so I didn't have a chance to show it. I can show it now. Yes, there are. Whatever you see here is actually API driven. So the ROC user interface is actually an API client. So whatever you can do from the user interface, you can do programmatically, exactly because, and this is our next step, and this is what we will be demoing next, is running an automated pipeline system like Kubeflow pipelines or Argo over our snapshots. So you can have full visibility on whatever the output of one step is and whatever the output of another step is. So you can go to each individual step of a pipeline and say, what does this step do? What did it have as input and what did it produce as output? Can I actually mount its input and its output so I can very easily have first-hand experience with what happened? This is great for debugging, by the way. It's full visibility into all steps of a pipeline by being able to retrace whatever every step did by mounting its immutable input and its snapshotted immutable output. So let me show it. This is James inside his environment. And he can actually access ROC programmatically and say, let me get my notes for this though. And he can say, let me create a new snapshot of my environment inside the James bucket. And at this point, this is an API call that we do to ROC. So this is the same thing that the user interface would show, but in a text tool, in a CLI tool. So demoing API-driven snapshots. Okay, just taking a snapshot using the API. Okay, so we submit this to Kubernetes, and again, a CLI tool, so totally automated, takes a snapshot of James's environment. And if we go into, so this is happening right now, right? I switch to the user interface and there's a new task that's actually progressing. So I used the API here to create a new task programmatically. And this task is what is running here. And this task is almost done. This task is almost done. This task is done. And yes, this task is done. Here are the immutable links I can use to access my snapshot. And this is it. I can now take this identifier, and this is an immutable permanent identifier that I can use to access my snapshot, so I can use it in pipelines programmatically. I hope this answers the question.
Awesome. Thank you. And thank you all for those great questions. That brings us to the end of our time today. So once again, thank you so much, Vangelis, for the great presentation, and to all of our attendees. Just as a reminder, the webinar recording and slides will be online later today. And we look forward to seeing you all in a future CNCF webinar.
Thank you. Thank you for giving me the chance to present.
Thanks, everyone. Have a great day.